Hi guys, in this video we are going to study support vector machines or SVMs. I'm sure you heard of SVMs and probably many of you have used them since they are such well-known models that work particularly well on problems of small to medium-sized datasets. They've been around actually for such a long time and so these are a type of supervised machine learning algorithms used for classification problems and occasionally for regression analysis too. These are quite popular, but as I mentioned, but on top of that, they are very elegant mathematically as well as computationally. In fact, by far one of my favorite algorithms for supervised machine learning. So the structure of this video is as follows. We're going to start by talking about the intuition of the method. What is the main idea and where it came from? As usual, some history. And then we will discuss it mathematically, its objective function and how it is optimized. You can skip this if you so prefer, absolutely fine. And then I'll talk about how linear support vector machines are applied to non-linear classification problems. And this is very important. And I will briefly introduce the concept of kernel tricks, and then we'll conclude with a few thoughts on when and where such models are useful. So as usual, suppose we have a two-dimensional linearly separable problem, red and blue observations, as you can see. That's a binary class or classification problem. If you want, you can look at the red observations as cats and the blue ones as dogs, if you will. That's again a binary classification problem. The two dimensions we have become therefore tail shape and weight. So these are the features. Nice. Now the question we put forward is the following. How many possible solutions can we have for a decision rule, or say a decision boundary actually, or a discriminator? In other words, how many models there can be to sort of separate the two classes? Well, in general, the answer should be many, in fact, an infinite number. I mean, this line does the job. This too makes zero classification on training samples, and this too does the job, right? You actually can think of any of these lines, or say hyperplanes in a higher dimensional problem, would be a good discriminator. They do separate samples relative to their labels. Actually, a perceptron of a neural net would pick any of these as a solution, and voila, that's it. But that is, in fact, very likely a suboptimal solution. Very likely. In other words, not perfect. And so, if it is likely a suboptimal solution, is it or will it indeed be the one you'd want to use as a decision boundary? Again, remember, we have many possible solutions. And if you want me to simplify this one more time, what I'm trying to say here is, if there is one unique best hyperplane or solution, which one is it of this infinite number of possible solutions? Well, the good news, there seems to be people who thought about it before us some time ago, actually quite some time ago, I believe in the 70s, I think. And these are the Vapnik and Chivrovenkis. And the story started from similar research by Vapnik and Chivrovenkis, I believe in the 70s, that led later on to the support vector machine. The support vector machine in particular came in the 90s, I think in 1995. But started with this type of analysis around a concept of complexity called VC dimension, which is one of many measures that characterize the expressive power or capacity of a hypothesis class. In fact, recently Vapnik liked to call it diversity rather than capacity in a podcast interview with Lex Friedman. Lex Friedman, I think, yes. But anyway, there's a few words to unpack here. A hypothesis class is a class of predictors. So it is, for example, one possible class is linear classifiers in d-dimensional space. That's one type of hypothesis class. Another type would be a degree k polynomial classifiers, and it's like zigzaggy, or curved lines. And you can probably guess, you know, which of these is going to have higher capacity. And then further complex is the hypothesis class of hierarchical access classifiers, which is what we saw with the decision trees, like greedy search-based algorithms. And we can go on and imagine lots of different ways to characterize classes of hypotheses. You have different sorts or categories of functions. And once you have the hypothesis class defined, the VZ dimension is defined by the ability of the hypothesis class to shatter n points. So what does it mean to shatter n points? It is like separating these points, observations, into the distinct classes without overlapping. So one more time. What does that actually mean? I mean, probably we better go and see how that relates to the best linear decision boundary in a d-dimensional space problem with our previous binary classification example. Let's see that. Here it is. So the linear SVM's basic idea, based on the linear function class capacity of shattering or splitting points, distinctively in the different classes, says, in a case of a binary classification problem, as the one we have here, remember we agreed that there must be an infinite number of straight lines to classify these well, right? You would want to trash all these possible linear discriminators except one which happens to be an optimal hyperplane, or in this case, optimal straight line. Remember, we are talking about linearly separable patterns or classes. And this one hyperplane that shatters the most points happens to have the largest margin around it from both classes or from both sides with no violations. But why would one argue that this must be the model you'd want to find? I mean, why is it the optimal hyperplane? And actually the intuition is simple. There is support for risk of misclassification. There is margin for error accounted for when you leave, the largest margin around this discriminator from both sides. So distinct class distributions can still expand towards the discriminator from both sides on unseen or say test data, and they wouldn't be misclassified. That is really a good solid point. Think of it with this simple analogy. The safest area to drive between obstacles from both sides is one that leaves some margin of safety on both sides, right? Well, that is exactly what support vector machine classifier or discriminator does, leaving a margin for safety for both classes to expand towards it without being hit or misclassified in the correct terminology. Okay, well, let's formalize this a little. First, let's see how does this work and what we need to actually learn. Let's first define the so-called support vectors. Basically, these are the data points that lie closest to the decision boundary or surface, or hyperplane if you will, from both sides. They are in fact the data points most difficult to classify. Makes sense, right? The closest opposite classes, but closest to one another, are the most difficult to classify. And they have as a result, of course, a direct impact on the optimum location of the decision surface. Again, makes sense. The closest points of opposite classes to each other must in fact define the boundary decision. Cool. Now the question, if there is such a beautiful hyperplane, how do we find it? Let's see. Well, first let's define one hypothetical hyperplane. Again, this is a straight line in a two-dimensional problem. And assume this must be the one hyperplane I want. I define it by the weights vector, W, or coefficients, because it's a straight line, just as a linear regression model, if you remember. Now, on this hyperplane, there is no training points. It is the boundary, right? So in essence, this means that x has zero value, i.e. observations has zero value. They don't lie on this hyperplane because it's a boundary. And therefore, I will have the line w times x plus b to equal 0, as you can see it. Fine. Now, what is that we need to find and how? Probably you guessed it, the hyperplane, or as on the figure, h sub 0 or h0, hyperplane 0 I call it, that has the largest margin around it with no violations, with no penetration of observations from both classes in this margin. Essentially, we are after the coefficients vector or w's vector for this straight line. Okay, if we want to find the largest margin, let's see if we could calculate distance to our hypothetical hyperplane from the closest data points or samples from both sides. With the largest margin for a non-violated, let's say, street, then you would want actually to see the closest point from both sides to this hypothetical hyperplane as a boundary decision. That is to say, I need to define a margin, well, ultimately the widest margin, so I need to calculate the distance to closest samples from both classes to these hypothetical discriminators, right? So if I say I define the two classes as positive and negative data points, and suppose I want to find a line whose W transpose X plus B equals 1, relax this for now, the 1 I mean, we will come to it later. And I will deem that as the margin at the positive side of the hyperplane where closest plus or positive points to the hyperplane lie. All I need is to calculate the distance from such points to the hyperplane. Well, I actually can do that from the point to line distance in Euclidean geometry, remember? It is the perpendicular distance of the point to the line. And okay, so this sounds very useful. I can project, say, for instance, on the upper side, the xi in red, I can project it on to the hyperplane h0, and the resulting vector is actually parallel to the w's vector. Now, this way I can calculate the distance between my hypothetical hyperplane and the closest samples, or say support vectors, on each side. Okay, well, this seems to become 1 over the weight's magnitude or norm because my hypothetical margin equals 1. So I hope this is clear to everyone. Now, there's a point here to consider about the 1, why these lines equal 1. Simple answer is for mathematical convenience. Not that because of the normalization of the weights vector norm in calculating the distance, the scale of W is basically arbitrary. So if we were to multiply W and B by some real scalar, alpha say, the factors of alpha in the numerator and denominator will cancel one another. And so now suppose that we choose the scale so that the nearest point to the hyperplane, xi in this case, satisfies W transpose X plus bias, or some bias, equals 1, then we can have closest distance to the discriminator is with the support vector being 1 over the norm of W. Take some time and digest this altogether. All I'm trying to say is that 1 can be any value. It doesn't need to be really 1. Now, I've skipped some maths actually, in fact, in my attempt to simplify this, but hopefully we are getting there. Now again, what we ended up having is that the margin on each side of, or the distance to the closest point to the hyperplane from each side of this discriminator is 1 over the magnitude of W, which means that the whole margin, both sides, must be 2 over the norm of the W vector. Okay, let's now see if we can find that hyperplane. Let me put it formally first and remind you, we actually want to do two things. We want to maximize margin around a hyperplane where there is no points observations on it. This one equals 0, this blue line. But also that this hyperplane needs to classify data points correctly. And think about it. This is really very important. Think about it. If it's only about the margin, the hyperplane can be useless for my classification problem. Think of a hyperplane on the moon, for example. It has actually the largest margin around it with respect to both classes, but it doesn't learn what I want it to learn. So my objective will have a constraint, right? It's like find a hyperplane with largest margin such that there is another parallel hyperplane on each side of the class, on each side of the hyperplane, where if the data point is of the positive class, it must either lie on the margin 1 or beyond. In other words, greater than 1. This is basically to say plus points can be either on the positive margin plane or beyond on the positive direction. Now, if the observation is the negative class, well, that means it should be less or equal -1, which is to say either on the negative samples margin plane, the blue one here, the thick blue, or beyond in the negative direction. Sweet. Now, to make things simpler, you can actually combine both constraints in one equation that looks like this one. Take a minute to think about it. Simple. If I multiply each of the equations above with the sign of each observation, this new equation must hold, because positive observation with the margin line of the positive side will get me either equal or greater than 1, and negative observation times the line that equals -1 should eventually give me greater or equal 1, because I need to multiply the -1 with -1 too. Okay, now what do we want again? Well, actually the largest margin, right? Again, if you remember, the distance is 2 over the norm of W. This is the distance, and this is basically 2 over the norm of W is the whole margin. So we want to maximize this term for W, which is basically to say we want to minimize the norm of W, right? It's the same thing. Well, precisely maximizing 2 over the norm of W is basically minimizing the squared norm of W. And we add this 1 over 2, or half, to basically make it easier to calculate the derivative. It is the same thing. Minimizing for a function or any scalar of that function is basically the same. And so if you look at this function, or call it now the objective function, what is it? It's actually a quadratic function. And, well, a quadratic function, that's true, but it's got a linear constraint. And this linear constraint is that, you know, each observation must obey this linear equation, right? And essentially, if you would want to translate it, is that each sample must be classified correctly at the right side of the hyperplane's margins. So it'd be looking at a constrained optimization problem to find this hyperplane. And because it is quadratic, the surface actually is a parabola, which means that there is just one single global minimum, or you can call it global minima. In other words, the objective function is a quadratic program, and quadratic program are one of those problems that are very, very well known and very well optimized methods to solve. I'll leave a quadratic problem, actually, a program with linear constraint optimization for you, but it's not required in our course. All I'm trying to say, or my main point here, is if there is a possible hyperplane that has got the largest margin around it, there is an efficient mathematical way of solving it. And it's completely more efficient than the perceptron, for instance, of the neural nets or the greedy search of decision trees. So now take a moment and digest all this together, and then let's go and see some properties of such a hyperplane relative to the different types of problems or, data sets that we commonly come across. For example, if you'd come across this case and there is an outlier is an observation which is misrecorded or wrongly recorded, or say noisy data, if you will, wouldn't that affect the choice for the optimal hyperplane? Remember, what the hyperplane is basically the straight line in this case with the largest margin around it. It certainly would. Now, on top of this or such potential problem, you will also have many problems or say data sets which will not be linearly separable. In fact, for the most part, you'll find problems like these. And as a result, there will be no way to satisfy all the constraints in the original objective function that we've just seen of what we commonly call the hard margin support vector machine, i.e. no violations, no penetration within this largest margin. And so the optimization gets infeasible, this optimization or objective function in such cases. And this happens, for example, if the class distributions are sort of overlapping and so cannot be linearly separable. So let's see if we could loosen this notion of largest margin without violations. So the idea of without violations, could it be changed? And whether that works, and if it works, well, that is brilliant, I would guess. And actually, Vapnik and the co-authors like Isabelle Guillon and Corina Cortez and I think Boser thought about it when they wrote their paper, I think machine support vector networks in the 90s. And they called it soft margin rather than the conventional hard margin. Let's look at that. So here's an example where you can allow for a wider margin whilst allowing for few violations. See how would the margin look like otherwise. So if you'd want actually to constrain it to the hard margin idea of support vector machine, i.e. no penetration within this large street or widest margin, then your hyperplane would look like this. If you'd want to look at them together, I will show you in a minute, but a stretcher margin certainly would be a result if you'd go with the hard margin. Is it better? Well, actually, probably not. Okay, let's look at it again. I would argue, actually, that the soft margin could allow for a better hyperplane. And that is on the basis of, say, few violations are not necessarily misclassifications, and yet you have much more support for margin for unseen samples. So now let's see how could we possibly find that. Probably you would have already thought, how could I optimize the objective function? It doesn't actually allow for such scenario, does it? It just tells me find the largest margin and you calculate the distance with the closest to the margin and you create the support vector, you call them support vectors, and voila, that's it. And then you align this hyperplane. Well, here's the deal. One way to cope with such problem and still learn useful classifiers is again to loosen some of the constraints by introducing the so-called slack variable. And here is yet another equation. I'll simplify it. Now these slack variables are introduced to allow certain constraints to be violated, which means certain training points will be allowed to be within the margin. We want the number of points within the margin to be as small as possible. And of course, we want their penetration of the margin to be as small as possible too. So a slack variable, xi, is introduced, one actually associated for each data point when you want to find the hyperplane. And so this psi is Greek letter. It's pronounced psi. It looks like this, but but it is without but. It's pronounced like psi. And so this variable is introduced into the optimization problem in two ways. First, the psi dictates the degree to which the constraint on the ith data point can be violated. So the psi is an associated value that dictates the degree or the extent to which the constraint of every data point can be violated. And second, by adding this slack variable psi to the whole function, we are actually aiming to simultaneously minimize the use of the slack variables, i.e. the violations. And so you can control the sum of these xi's with a tunable parameter, which is c, as you can see here. And think about it like this. It's like adding a penalty term. More violation or penetration for a wider margin, or a smaller margin with less violations. That becomes actually the optimization problem. So you'd find it if C is big, say, for example, that's to say that the optimization will prioritize psi, because C is magnifying the sum of violations or the associated violations, the associated extent of violations, which means you will pay for that in the width or from the width of the margin. And on the contrary, if C is small, you're basically saying don't bother with the violations. I mean, just minimize their weight, their significance, just find a wider margin discriminator. And so think about it. If C is 0, for instance, then effectively that's the original hard margin support vector machine, but allowing for violations, because in the optimization problem, you're having the linear constraint is no more greater or equal 1, but 1 minus this associated, slack or psi relative to each observation. And then we practically do the whole optimization. We usually use the cross-validation and see which C performs best on the different test sets. And just another side note here, psi is usually greater or equal 1 for misclassified points, because you need to assign it to each point whilst training the support vector machine. And usually it is between 0 and 1 for points close to the decision boundary. If you want to visualize how it works, here you can see it, the effect of C on the optimization of all the optimization of the objective function, See, when C is small, we move in the direction of wider margin and to a stretcher margin otherwise if C is big, large. Okay, now that we spoke about soft margins, let's tackle yet another data problem. And that's where you have distributions which are not separable linearly, or it's impossible to separate classes with a linear hyperplane. And in fact, in such problems, there's in fact no way for a hyperplane to become a useful classifier. Look at these examples. You cannot separate two classes here with a hyperplane or straight line. So a univariate problem on the left and a two-dimensional one on the right, no straight line whatsoever to do the job, right? Is there anyone you can suggest? Of course there isn't. But how if we deal with it differently? And here's the example. So if the data is not linearly separable in the original I mean the original feature space or input space, then we apply transformations to the data, which map the data from the original space into a higher dimensional feature space, as you can see. So for instance, the first one goes from one-dimensional space on the left to a two-dimensional space. And the second goes from two-dimensional space to a three-dimensional problem. And so the goal is that after the transformation to the higher dimensional space, the classes are now seemingly linearly separable in this high dimensional feature space. We can then fit a decision boundary to separate the classes by the support vector machine, i.e. a hyperplane, d-1 hyperplane. And so the decision boundary will be a hyperplane in this higher dimensional space. So here's an example. You would agree with me that there's no such a hyperplane to separate the two classes or the two class samples, right? The samples of the both classes from one another. However, if you add another feature, and this happens to be feature 1 squared, for instance, you'll find visually that you can actually come up with a two-dimensional or a 3D, in fact, here, but it's like a straight, a linear hyperplane. You can call it like sort of augment, but be careful with the augmentation here. Or better said, transform the original space into a higher one. And so you can have a d-1 hyperplane that is linear and yet does the job, right? This is actually beautiful, and this is how the discriminator looks when projected again onto the original feature space. Look at this. In the original dimensionality, it is actually nonlinear. So I'm referring to this one that you can see here, and I reproject the hyperplane as well as the observations to the two-dimensional problem that I had initially, and look at how the hyperplane looks like. It's nonlinear, it looks more complicated than a straight line, but it does the job. And it seems powerful, right? Okay. We have seen how higher dimensional transformations can allow us to separate data in order to sort of make classification predictions, right? It seems that in order to train a support vector classifier and optimize our objective function, we would have to perform the sort of operations with the higher dimensional vectors in the transformed feature space. In real applications, however, there might be many features in the data, and applying transformations or many features, many observations that involve many polynomial combinations, for instance. We talked about a square of feature 1, for instance, or cube or whatever. And so these transformations will lead to extremely high and practical computational costs, right? Well, there seems to be a way around it, and this way is called the kernel trick. And so the kernel trick is sort of a function or way that provides a solution to this type of problem. The trick is that kernel methods represent the data only through a set of pairwise similarity comparisons between the original data observations, with the original coordinates in the lower dimensional space. That's instead of explicitly applying the transformations and representing the data by these transformed coordinates in the higher dimensional feature space. There's some maths here, so I'd relax it for another video. Bottom line, however, you can get to a hyperplane in the higher dimensional space without the need to explicitly transform the features into a higher dimensional space. That is what is called the trick, okay? And that is done through functions which are called kernel functions. And of the many trick kernels that we have, well, there are many kernels, in fact, which I would suggest for you to look at. For instance, there are polynomial kernel, Gaussian kernel, Laplace RBF or radius basis function kernel, sigmoid kernel, etc. And actually, I will refer in the pros and the cons about that method that there is a problem sometimes in optimizing or finding actually the right kernel function. Now, I'll conclude with a few notes around where support vector machines seem to be good. They've been widely applied and used all over the place since the 90s. In fact, before that deep learning eruption, they were actually the place where to go because they are interpretable, they are beautiful, efficient, and they work well. And so they are very effective in high dimensional problems, and in fact also very effective, and they work when that number of the features is more than the number of the samples. And not many algorithms can find actually reasonably or good discriminator, or say for instance probabilistic methods or models. They need a lot of observations to make generalizations, whereas support vector machine just finds this global minima to the function. And it is the best algorithm when classes are separable. I showed you that when by creating the largest margin, you find that this is, you actually can ensure that this is the unique, best, optimal separator or decision rule. And it's happy with outliers if you would allow for the soft margin version of support vector machine. And it also does regression, which I didn't cover, but eventually it basically reverses the idea. It's provided in most off-the-shelf libraries, including the scikit-learn, but actually it is the opposite of the discriminator for classification. You would want to find the smallest margin with all the violations in between in this stretch road rather than off the road. Now, on the other side of the coin, you have the support vector machine for larger data sets. It requires a large amount of time to calculate and process, especially because you have basically, you'll end up having many support vectors and many violations. So the optimization problem becomes a bit more exhaustive. And it does not perform as well in cases of overlapped classes, because again, that adds a burden to the optimization problem with the soft margin. And then selecting appropriately hyperparameters for the support vector machine that will allow for insufficient generalization performance can be tricky. And that also relates to, because you have the slack variable that is associated to all observations. If the data set size is big or very big, then that means there are so many variables or many observations that have an associated psi. And then you need to optimize the best C, this tunable parameter that controls that penalty. And likewise, selecting the appropriate kernel function can be tricky. That's all. I leave you with these references for you to look at. The Aurier-Geron Hands-on Machine Learning. This is the first edition. And you can also look at the documentation provided. I mean, some of it is referring or citing the original work of the Vapnik et al. And here, if you are going to miss it, Cortis, Corina, and Vapnik, Vladimir support vector networks, and I think this is the one of 1995. And I supplied this material also on Blackboard. Thank you very much, and I hope you liked it.